Okay, so today we're going to start covering cyclohexane molecules more in depth, and we're going to start talking about what's called substituted cyclohexanes. And we're going to talk about the repelling forces between a substituted cyclohexane and the hydrogens surrounding the carbons on that cyclohexane. And these forces are called diaxial repulsions. And we're going to talk about how it relates to the equatorial ring flipping process. Okay, so now that we know that cyclohexane is constantly in this ring flipping process, in which this chair, if we label it chair number 1, for example, chair number 1, and this chair, which will denote chair number 2. Now that we know that a cyclohexane molecule is in this constant back and forth between these two forms of its chair molecule, we can start to now analyze the ratios in which both of these cyclohexanes appear. And on unsubstituted cyclohexanes, meaning that there is nothing but hydrogens attached to each carbon of the cyclohexane molecule, we will see equal 50-50 ratios of the presence of both of these chairs in the ring flipping process. What happens though if we start to deal with what's called in organic chemistry monosubstituted cyclohexane chairs? And the name tells you everything that you need to know about what that is. Mono means one, and substituted just means any carbon that has something other than a hydrogen attached to it on the cyclohexane molecule. If we start to look at the ratios during the ring flipping process for substituted cyclohexane molecules, then we're going to see that it starts to change. What I mean by that is if I put a methyl group on this hydrogen, on this axial hydrogen instead of the hydrogen that was originally there, and you can substitute it with anything. It doesn't have to be a methyl group. It could be a bromine or a ethyl or a butane. But yeah, if I substitute it, what we're going to start to see is that, assuming that we label this as the first carbon right here, depending on where we count from, whether we count from right to left or from top to bottom, we will see that there are two spots on the cyclohexane molecule that can be considered the third carbon, and each of those third carbons has an axial hydrogen attached to it. So once again, let's label this as the second carbon, this as the third, and then counting from right to left instead, we'll label this as the second carbon and this as the third. So you see two spots where there is a third carbon on the cyclohexane molecule, and both of them have these axial hydrogens, as well as an equatorial. But if we also notice that there is a hydrogen on the now substituted methyl group on this as well, what we start to see happen is that this hydrogen is going to start feeling a repulsion from this hydrogen, and this hydrogen is going to start feeling a repulsion from this one as well. And what that means is that you are experiencing a repulsion between a hydrogen on a methyl group on the first carbon, and that those repulsions are being caused by the two hydrogens on the third carbon, the two axial hydrogens on the third carbon. And that's why we call it 1, 3, di meaning 2 for the two axial hydrogens, diaxial repulsion. And that's a phenomenon that causes this methyl group to now want to ring flip, or prompts the entire cyclohexane molecule to now want to ring flip, because it just so happens that when this methyl group or any substituent that isn't a hydrogen on the cyclohexane molecule is in the equatorial position, it interferes less with the other hydrogens around it bonded to the carbons of the cyclohexane molecule, and therefore causes less repulsion. So since this methyl is here on the axial position, it's going to want to go into this equatorial position, and then we'll see something like this instead, where the methyl group is attached to the equatorial position on the cyclohexane molecule, and we're going to start to see this chair now, the equatorial one, with about 90% of the time spent during the ring flipping process, as opposed to 10%. So it's important to remember that monosubstituted cyclohexanes will always put their substituent, which is larger than any of the hydrogens around it, attach the carbons of the cyclohexane molecule into the equatorial position. That's important for when we get into disubstituted cyclohexane molecules. Since we now know that substituted cyclohexanes want to put the larger substituent groups onto the equatorial positions on cyclohexane molecules, what starts to happen when we see disubstituted cyclohexanes, or cyclohexanes that have more than one substituted carbon containing something other than a hydrogen? Well, for this we have to use a plane of symmetry, kind of like we did in a couple videos back. And so we'll take something like this, for example, and we'll create a plane of symmetry in which this cyclohexane molecule is going to be cut in half, so to speak. So now we can cut this cyclohexane molecule into two halves, being the upper portion or the lower portion down here. So now we split this molecule into two sections where we can have what's called here, for example, an up axial hydrogen, up axial, or we can have a up equatorial, because it's coming out of the plane of this barrier that we just made to split them. Can be an up equatorial, or this right here can be a down equatorial, right? Because it's going down out of the 3D separation barrier that I've just made here on this molecule. Depending on whether or not the substituents are all on the same plane, whether they be axial or equatorial, we refer to them, and this is a little bit of nomenclature, we refer to them as either being cis or trans. Cis meaning on the same side, and trans meaning on opposite sides of the plane that I've just created on this molecule. What do I mean by that? It means that, let's say we have a methyl group here. We write a CH3 here to represent a methyl group on this carbon here. And let's say that we have a methyl group here as well on this equatorial hydrogen here. So we'll draw another CH3. Both of these substituents are considered going up, even though one is axial and the other is equatorial. Both of these are coming out of the plane, upwards out of the plane that we just drew on this molecule. So these two substituents on the cyclohexane molecule would be considered cis to each other. Cis. If we had, and now I'm gonna switch colors for a second. If we had, for example, one CH3 here on this part of the hydrogens on the cyclohexane molecule, and we had another substitution here, we'll draw another CH3. These are also cis, but they're cis down. Now if we had one CH3 here, for example, and we removed this CH3. So if we had a CH3 on this hydrogen, substituting this hydrogen, and a CH3 substituting this hydrogen, these molecules are now trans to each other because they are coming out of different planes on the cyclohexane molecule when we look at it in this form that we're considering it split in half. And that's just a convention that we came up with to be able to specify where these substituents are in reference to each other on the cyclohexane molecule. So to do a quick recap, what do we know? Well, we know that substituted cyclohexanes will always look to put the bigger substituents on the equatorial position. So bigger, we know that one, bigger favors equatorial. We know that depending on where these substituents end up, because they favor equatorial, we can denote them as being either cis or trans to each other. Cis or trans. And so with this information, we can start to name cyclohexanes or substituted cyclohexanes by their names alone. So if I were to tell you that I want you to tell me what a molecule named I don't know, trans Let's do trans 1,1-butyl 3-methyl cyclohexane. Looking at this generic cyclohexane molecule, how would you now draw trans 1-butyl 3-methyl cyclohexane? Well, the first thing that you should ask yourself is which one of these carbons contains the bigger substituent. Now we see that there is a 1-butyl here, and we have a 3-methyl, meaning that we have a butane attached to one of the carbons and a methane attached to one of the carbons. Butane has 4 carbons, methyl has only 1. So with that information, we can now deduce that without a doubt, the butyl group is going to be on the first carbon, because we have 1 butyl, and since butane is the bigger group as opposed to methane, then butane is going to be the one that's going to take the equatorial position on this molecule. All right, so it's going to go here, or we can draw it here. Okay, so now we have one molecule. We know that it has to go on, or I'm sorry. This is going to be the butane. So this is going to be 1, 2, 3, 4 carbons. Sorry about that mistake. So we have 4 carbons coming off of this on the equatorial position. I should have actually drawn that in blue. Let me switch that to blue. Right, so we have a butane representing 4 carbons coming off of that. We know that the methyl goes on the third carbon, so if we're counting this as the third carbon, saying 1, 2, 3, if we're counting this as the third carbon, we know that now the methyl group, since it's a smaller substituent, has to go on the axial position. Not only that, but it's on the trans. It's on the trans, so you know that it has to be axial up. So we'll put our CH3 here. And that's basically how you name disubstituted cyclohexane molecules. You look at which one is the bigger group, you put it on the equatorial, and depending on whether or not it says cis or trans, you put it where it's supposed to go, whether or not it's going to be coming up out of the plane of the paper or down away from the plane of the paper, due to the splitting in half of the molecule that I showed you earlier.